Good day everyone. I am Noah Millicent Ortega from BSECE 5B of Laguna State Polytechnic University, San Pablo City Campus. I am here to present my work about microwave link design made by me. Yeah. And this will be submitted to Engineer Conrado Camilon. Let's start. Okay, hello everyone. Before I start my report about microwave link design, there are things and terms that you need to know before I discuss all of my design. Yeah. And one of them are microwaves. Microwaves can propagate through a guided medium, such as a transmission line, which could be a cable or a waveguide. They can also propagate through an unguided medium, as plane waves in free space and through the atmosphere. The second one is microwave communication or transmission. It involves the sending and receiving of microwave signals over a microwave link. This microwave link is made up of a string of microwave radio antennas. They are often located at the top of towers at various microwave sites. What is a microwave link? Microwave link is a line-of-sight wireless communication technology that uses high-frequency beams of radio waves in the microwave frequency range to provide high-speed wireless connections that can transmit and receive video, audio, or data information between two locations, which can be from just a few feet or meters to several miles or kilometers apart. And microwave links are widely used for point-to-point communications because their small wavelength allows conveniently sized antennas to direct them in narrow beams, which can be pointed directly at the receiving antenna. This allows nearby microwave equipment to use the same frequencies without interfering with each other, as lower frequency radio waves do. Another advantage is that the high frequency of microwaves gives the microwave band a very large information carrying capacity. The microwave band has a bandwidth 30 times that all of the rest of the radio spectrum below it. Next, what is a microwave link design? It is a methodological, systematical, and a very long process in telecommunication industry. It includes loss or attenuation calculations, fading and fade margin calculations, frequency planning, interference calculations, and availability calculations. These processes are very important in microwave link planning for the establishment of a reliable microwave link which contains expensive hardware components. Yan. We'll start here, the applications of microwave link design. Number one is studio to transmitter links for radio and television broadcasting. Second one, head ends to distribution system of many cable TV. Third one, point-to-point links as a backbone or tails of large networks for private and government entities. Fourth one, point-to-point or point-to-multipoint systems for TV, telephony, and data. Fifth is air traffic control center interconnectivity. Sixth is short-haul applications such as linking offices and buildings in congested urban areas. And the last one is military applications. What are their advantages? Number one is it does not require right-of-way acquisition between stations. Second is it requires purchase or lease of small area of land only. Then it can carry large quantities of information. And it requires relatively small antennas. Then signal can be easily propagated around physical obstacles. And underground facilities are minimized. Increased reliability and less maintenance. What are the steps in link engineering? Site survey. Site ocular, which includes weather, wind velocity, soil pressure, access roads, and aerial photograph. Path profiling. Needs topographical map to read contour lines and determine elevation between two sites. Type of terrain, earth bulge, K-factor, and Fresnel zones. Link budget calculation. It involves equipment parameters, frequency selection, and assignment. Appropriate radio equipment to determine required transmitter power and threshold power. As we can see, the first step in link engineering is site survey. I will show you my site survey. I chose this place, Pasig City, Metro Manila, which I will place my transmitter. These are the coordinates, the latitude, longitude, elevation, terrain. As you can see, all of this information are written here, all of the data. Yeah. Elevation 5 meters, terrain suburban, nearest access roads 31.10 meters, the facilities, main power source, Meralco, secondary power source, generator, cellular phone system, Smart, Globe, Torque, Sun, Gonzon, Fullerobel, Binbit. Peace and order. In Pasig City, 93.83% crime solution efficiency rate. Presence of airport, none. Nearest bodies of water, Pasig River, 452 meters away. Weather condition, temperature 26 degrees Celsius to 33 degrees Celsius. Rainfall rate, about 669 millimeters. Telephone and telegraph services, there are a lot. PLDT, PTNT, Nextel, Exanet, Converge, EXI, Elora, Radius, DPG, Digital, Asia Telecom, Belfort, GBS, Chin, and Telephilippines. And this is the place where I will put my receiver in Dasmariñas City, Cavite. As you can see, I will place it there. Yeah, the coordinates. This is its latitude, longitude, elevation 72 meters, terrain, fields and sparse houses, nearest access roads 35.52 meters, facilities, main power source, Meralco, and secondary power source 2 is generator. Cellular phone system, Smart, Globe, Sun, Telnovo, and Bahon. Peace and order here in Dasmariñas City, Cavite. 75.94% crime solution efficiency rate. Presence of airport, Orchard helipad. Nearest bodies of water, none. Weather condition, temperatures are from 26 degrees Celsius to 32 degrees Celsius. Rainfall rate, about 593 millimeters. Telephone and telegraph services, PLDT, JAQ, Marinao, Converge, Digital, Asia Telecom. And the second one in link engineering steps is the path profile. Microwave signals are affected by conditions of possible obstructions, reflections, atmospheric conditions, and the curvature of the Earth. The curvature of the Earth, or Earth bulge, should be considered in planning a microwave system. It is very important to consider it. These are the steps in making a path profile. Calculate the earth bulge at maximum elevation. Determine the total obstruction. Calculate the first Fresnel zone, or ZN, at maximum elevation. Calculate the tower heights. Assume equal. Using the path clearance equation, consider 60% as minimum path clearance. Calculate path clearance. Verify Fresnel clearance ratio greater than 1. Determine line of sight clearance from the first Fresnel zone. The first and second one were calculate the earth bulge at maximum elevation and determine the total obstruction. We calculate the K factor, or K. This is the formula. K is equals to 1 minus 0.04665 e raised to 0.005577 ns. This factor, an equivalent Earth radius factor, conveniently defines the degree and direction of bending. This factor, or K factor, multiplied by the through Earth radius r, is the effective Earth radius, or the radius of a fictitious Earth curve. Any change in the amount of beam bending caused by atmospheric conditions can be expressed as a change in K. How do we get the effective Earth radius, or RE? It is equals to KR, where R is equals to the through Earth radius, which is 6,370 kilometers. K is equals to the K factor, and S is the surface refractivity. Ns is equals to 300, for K is equals to 4 over 3. Surface refractivity, or Ns, is equals to No times E raised to negative 0.1057 hf, where No means sea level refractivity and Hs means elevation of link above sea level. These are the constants. K is equals to 165 in a mountain. In rice paddies, 2 over 3. 4 over 3 in dry rock or standard. In water, 0.58. And in coconut trees, it is 3/4. And this is the averaging of the K factor. K1, D1 plus K2, D2 plus etc. Then until we end up in a Kn, Dn all over D. Representation of the relative curvature. Curved Earth, straight line beam approach. A representation of a curved Earth with effective Earth radius, or Kr, and the straight line microwave beam. This is a straight beam and the curve of the Earth. Flat Earth, or curved Earth beam approach, a representation of a flat Earth with a microwave beam having curvature of Kr7. As you can see, this is the curved beam and the flat Earth compared to the straight beam and the curved Earth. Then we'll talk about the Earth bulge. This is the general equation. Metric system, Ht in meters is equals to D1 in kilometers, D2 in kilometers also, all over 12.75 K. If D1 is equals to D2 is equals to D. Ht in meters again, D in kilometers squared, all over 12.75 K. In English system, the Ht in meters is equals to D1 in miles times D2 in miles, all over 1.5 K. And if D1 is equals to D2 is equals to D, Ht in meters is equals to D in miles squared, all over 1.5 K. If K is infinity, the so-called Earth bulge, or the curvature, is 0. H is equals to 0 at this value of K. The microwave beam follows the curvature of the Earth. Then, if flat Earth, there will be a straight beam. Letter B, if K is equals to 4/3, this is the value of K under normal atmospheric conditions. In metric system, Ht in meters is equals to D1 times D2 in kilometers, all over 17. And if D1 is equals to D2 is equals to D, Ht in meters is equals to D squared in kilometers, all over 17. In English system, Ht in meters is equals to D1 times D2 in miles, all over 2. And if D1 is equals to D2 is equals to D, Ht in meters is equals to D squared in miles, all over 2. The third, fourth, and fifth steps in making a path profile are calculate the first Fresnel zone or the CN at maximum elevation. The second one is calculate the tower heights. Assume that they are both equal. Using the path clearance equation, consider 60% as minimum path clearance. The last one is calculate the path clearance, verify Fresnel clearance ratio. That should be greater than 1. Fresnel zone and Fresnel zones are series of concentric ellipsoids that surround the path form from the transmitter to the receiver. As you can see, this is the Fresnel zone. It surrounds the path from transmitter to the receiver. The first Fresnel zone is the surface containing every point for which the sum of the distances from that point is exactly 1/2 wavelength longer than the direct path. Fresnel zone radii are radii of the concentric circles corresponding to the cross-section of a particular Fresnel zone. A. Fresnel zone concept. If a reflected path is bounced within an odd-numbered Fresnel zone, it would arrive at the receiver in phase addition with the direct signal. The field at the receiver is thus at maximum value. If a reflected path is bounced within an even-numbered Fresnel zone, it would arrive at the receiver in phase opposition with the direct signal. The field at the receiver is thus at minimum value. Letter B. First Fresnel zone radius, or the F1, in metric system, F1 or first Fresnel zone radius is equals to 547.1 square root of D1, D2 in kilometers over F frequency in megahertz and D in kilometers also. And F1 in meters, 17.3 square root of D1, D2 in kilometers over F if you use gigahertz, and times D in kilometers. In English system, F1 in feet is equals to 2,260 square root of D1, D2 in miles over F megahertz over times D in miles again. F1 in feet again is equals to 72.1 square root of D1 times D2 in miles over the frequency in gigahertz times D in miles. Letter C. Nth Fresnel zone radius, Fn. Fn is equals to F1 square root of n. Fresnel zone clearance, or FC. It takes into account the unusual conditions that occur in the atmosphere. FC is equals to 0.6 times F1. Path clearance equation, big H, is equals to small h1 minus h0 plus d1 over d times h2 minus h1, where this h is the path clearance, this ho is the total height, EB plus E plus earth plus tree growth, h1 this one, earth elevation plus tower height at site 1, h2 this one, earth elevation plus tower height at site 2, and d1 this one, distance from site 1 to HO, and this D is the total distance. Determine the line of sight clearance from the first Fresnel zone. Line of sight formula at maximum obstruction, or LOS, is equals to H plus HO. Clearance from the first Fresnel, C first, is equals to LOS minus HN plus HO. HN is equals to FN, and Fresnel zone radius. This is my path profile graph. As you can see, this one is the LOS. This is the earth bulge. Elevation, this is the elevation. Oops. This is the total obstruction. Then this is the LOS, lower frequency. upper frequency, upper FC, and the lower FC. You can take a look, take a picture or anything. This is the elevation, and it is in meters by 10. Its increment is 10. Then in the x-axis is the distance in kilometers. Yeah. 0 to 29 because my distance is 27 kilometers. This is the Pasig, Metro Manila, up to Dasmariñas, Cavite. This is my tower 1 and this is my tower 2. But path profile data, based on the formulas and equations that we used before, that we have seen before, this is the data, that the informations that I gathered based on those formulas. And yes, this is the D1, D2, K, K factor, earth bulge, elevation, terrain, additional obstruction, total obstruction, F1, FC, 27, H1 minus H1 to H0, H2 to H1, yes, upper Fresnel zone, lower Fresnel, upper FC, and lower FC. And yes, you can take a look at the data. Next, this is the other way in making a microwave link design. Equipment selection. The equipment selection process is considered in the early stage of the design process because it decides the quality, cost, and reliability, which are important for the client's satisfaction and needs. Equipment selection. The first one that I chose is the FGR2 series, 900 megahertz industrial radio. Its transmitter power is 30 dBm and its sensitivity is -107 dBm. This transceiver satisfies the 1+0 configuration required and covers the frequency band used in the design. Example, 13 GHz. In addition to this, it can also accommodate E1 trunk lines, which are required in the design, and covers also commercially available antenna sizes. It has a two-level GFSK modulation, 115.2 kbps or 153.6 kbps. Second one is the antennas. Its diameter, its gain in 4 feet, 41.8 to 42 dBi. Operating frequency 12.7 to 13.25 GHz. Then waveguides. Waveguide size, I chose WR75. Its frequency range are 10 to 15 GHz and its attenuation per 100 meter is 25.26 decibel. Connectors. Waveguide size, again, WR75. Its frequency range, 10 to 15 Hz. And attenuation per 100 meter, 0.25 decibel. The other one, WR75, 10 to 15 gigahertz. And 0.25 decibel. Circulators, waveguide size, again, WR75, frequency range, 10 to 16 Hz and 10 to 15 GHz. Attenuation per 100 meter, 0.25 decibel and 0.25 decibel again. In radomes, operating band, KU band, 12 to 18.5 GHz. And its radome loss, 1.1 decibels, and both are the same. Frequency planning. The distance that I required for us to make is 25 kilometers in at least. So I made 27 kilometers. I chose 27 kilometers because that is the distance from the Pasig City, Metro Manila, up to Dasmariñas, Cavite. Its frequency band, you will choose here and its maximum distance allowed. We are using 27 kilometers at distance, so here here we are in between 15 to 30 kilometer. That's why we can choose in these frequency bands, 13 or 15 or 18 gigahertz, and I chose frequency that is 13 gigahertz. And yes, this is the frequency that I use, 13 gigahertz band. F is equals to FO minus 259 plus 28N, and we'll compute it. F3 is equals to 12,769 megahertz or 12.769 gigahertz. And yes, this is the other one. And it results in 13,035 megahertz or 13.035 gigahertz. And this is the channels F1, F2, F3, and F4. Link name AR, RA, RB, BR. Directions go, return, and frequency gigahertz. These are the frequencies, as you can see. Link budget, this is the last part, I guess, in making a microwave link design. It is the summary of gains and losses, and it is used to determine the system's reliability. Link budget parameters. I'm about to discuss the losses. Total losses is equals to FSL, TLL, ALL, FM, MPL plus other losses. All the losses that we'll encounter. First one is the free space loss, or the FSL, or path attenuation. It is the loss that will be obtained between two isotropic antennas in free space, where there are no ground influences or obstructions. It is also defined as a loss incurred by an electromagnetic wave in a straight line through a vacuum with no absorption or reflection of energy from nearby objects. This is the general equation of free space loss. FSL, or L sub Fs, is equals to quantity for pi d over lambda, or the wavelength, quantity squared, where the d here is the path length in meters, and the lambda is equals to the signal wavelength in m. Free space loss in decibel. These are the formulas, metric systems. In metric system, FSL is equals to 32.4 plus 20 log F in megahertz plus 20 log D in kilometer, or FSL is equals to 92.420 log F if your frequency is in gigahertz plus 20 log D in kilometers. In English system, FSL is equals to 36.6 plus 20 log F in megahertz plus 20 log D in miles. FSL is equals to 96.6 plus 20 log F in gigahertz plus 20 log D in miles. Transmission line loss is equals to TLL, antenna height A plus antenna height B plus waveguide length times the TL loss multiplier. Atmospheric absorption loss due to oxygen at frequency below 57 gigahertz. These are the formula, and the formula in absorption due to water. This one is the formula. Next one, the fade margin in decibel. It is a fudge factor included in the system gain equation that considers the non-ideal and less predictable characteristics of radio wave propagation, such as multipath propagation and terrain sensitivity. It is an attenuation allowance so that anticipated fading will still keep the signal above specified minimum radio frequency input. These are the formulas in metric system. These are the formulas in English system, as you can see, where R is the propagation reliability. The values for A, this A here, it is the values of for A. For if the roughness factor is for very smooth terrain over water, flat desert, 1.0. For average terrain with some roughness, 0.25 for mountainous, very rough, or very dry terrain. Values for B factor, here, this one. To convert a worst month probability to an annual probability. 0.5 for hot, humid coastal areas, 0.25 for normal interior temperate or subarctic areas, 0.125 for mountainous or very dry but non-reflective areas. Other losses from the equipment manual, the hybrid loss, coupling loss, connector loss, and radome loss. Link budget parameters in gains. The last one was in the losses, and this one is the gains. Total gain is equals to total loss minus transmitter power plus sensitivity. Parabolic antenna gain, or G, is calculated as the gain over an isotropic source. Parabolic antenna gain for typical values, 0.55 to 0.75 metric system. These are the formulas, as you can see in the screen. Received signal level, or RSL, in dBm, RSL is equals to, as you can see, where LTX and LRX is the transmitter and receiver, total insertion losses in decibel, GT and GR transmit and receive antenna gains in decibels, LFS free space loss in decibels, FM for fade margin in decibel, PO in dBm, the transmitter output power. This is the visual representation. And then system gain in decibel. This is the formula where PO in dBm is the transmitter output power, and the threshold receiver minimum radio frequency input in dBm. System reliability estimates, non-diversity systems, reliability R, or availability. This is the formula where this D is in kilometers, and this F is in gigahertz. Reliability should be greater than 0.99999 or 99.9999%. If not, use diversity techniques. Diversity systems, reliability, R, or availability, R is equals to 1 minus UDIV times 100%, where UDIV is the diversity annual outage probability or the fade probability. Diversity outage or fade probability, UDIV, is equals to UNDP over IDIV, where UNDP is equals to non-diversity annual outage probability or fade probability. IDIV is a diversity improvement factor. And these are the data that we gathered in making our link budget. From our path profile, these are the informations. Distance between the towers are 27 kilometers. Antenna heights computed. The first one is in 25 meters and the second one is in 20 meters. The frequency that we chose is 13 gigahertz. Elevation of the two sites, 5 meters and 74 meters. Assumed values, reliability is equals to 99.9999%. Proposed values, the transmitter power that we use, 30 dBm. Sensitivity or the RTH is equals to negative 107 dBm. And total losses that we got is equals to negative 26.71 decibels. These are the data or the information that we gathered in making our link budget. As you can see, the connector loss, LC, it is constant because it is based on the specification that we use. These are the values, these are the units, and we compute some of them, like the total loss, the total of all these losses, and this is the result. The frequency, and if we compute it, yes, this is the equations or the computation, and these are the calculations or the results of those equations that we used. These are the parameters that we used. In transmitter, we got the output power antenna gain, effective isotropic radiated power, free space loss. Here are the equations again. Uh, by the way, these are their symbols. And yes. And in the receiver, we got the antenna gain, the new antenna gain, antenna diameter, received signal level, receiver sensitivity, fade margin, UNDP, and the reliability. In conclusion, in everything, because of congestion in the radio frequency spectrum, it raises the use of microwave communications. At present, microwave link is the common mode of communication due to its advantages than those using radio frequency communication links. Some of the advantages that this mode of communication offers are increased bandwidth and higher speeds. The signals are also easily propagated around physical obstacles, and it does not require physical facilities. However, it also has its disadvantages, of course. It is difficult to set up because there are many factors to be considered, such as the terrain of the signal propagation path, reflective terrain surfaces, the different space interferences, power budget, and the equipment to be used. Based on the study conducted, after considering the different factors that could greatly affect the system, the designed microwave link is working both for standard Earth and for abnormal bulge of the Earth. And my recommendation in making a microwave link design, it is indeed a difficult process in designing microwave link. Yes, it's very difficult, it's very hard. So for future works, I recommend to those designers or engineers that will design their own microwave link that they should choose to shorten the path link between the sites, since Earth bulge in between becomes higher in value when the hop is large in value, and this may cause loss of line of sight in the design. Also, when choosing the sites, terrain between them must not contain any dominant obstacle between them. But all in all, preliminary knowledge on several concepts and formulas will make your design easier to make. Again, I am Noah Millicent Ortega. Reporting discussing my microwave link design made by me, Noah Millicent Ortega. Yeah, thank you.